Hello, my name is Pushpita Chanda. I am a PhD student at IIT Delhi under IIT Delhi and University of Queensland Joint PhD program. I am the TA for this course, Applied Optics. So today I'll discuss for assignment number 4, which are due is this Wednesday. This is module 4, and in this module the professor has discussed interference of light waves and mainly the interference by division of wavefront. So let's begin the class. So first get of the class, what in the five lecture from lecture 16 to 20 has been discussed. So basically, what is interference? So basically, interference of light waves is this corresponds to the interaction of two or more light waves yielding a resultant irradiance that deviates from the sum of the component irradiance. That basically I is not equal to I plus I1 plus I2 always. Or we can write it like this. So this 1 to infinity. So we have seen that interference is basically like two wave interfering, but it can be more than two waves. And we need to always remember that we will talk about irradiance, the electric field. So basically the optical disturbance of electric field varies in time at an exceedingly rapid rate, that at 10 to the power 14 hertz, that it is very impractical to detect the actual field, but it is very much possible to detect the irradiance. So we will always talk about fringe width in terms of irradiance. So now we are considering two wave. E1, which is a function of R and T, and also E2, which is a function of R and T. So E1 is E01 cos K1 R minus omega T plus epsilon 1, and this is E02 cos K2 dot R minus omega T plus epsilon 2. Epsilon 1 and 2 are the initial phase, K is the phase vector. So you know the drill that you need to add E1 plus E2, and for irradiance we need to take a whole square. So after doing all those things, I is basically E square and I1 is basically E1 whole square, and I2 is E2 whole square, and we got to know that I is I1 plus I2 plus 2 into root over I1 I2 cos delta. Delta is phase difference. So for this wave, delta is basically k1 dot r plus epsilon naught minus k2 dot r minus epsilon 2. We can write it as a k r1 minus r2. Okay, sorry. Or we can write it here k r1 k r2. K r1 minus r2 plus epsilon 1 minus epsilon 2. This is the phase difference, initial phase difference, we can say that. So I can become I1 plus I2 plus 2 root over I1 I2 cos is delta by t when I1 is equal to I2 is equal to I, it became 2I plus 2 into I cos k r1 minus r2 plus epsilon 1 minus epsilon 2. Can be written as cos delta by 2, which can be written as 2I naught cos square delta by 2. So 2I naught cos square half k r1 minus r2 plus epsilon 1 minus epsilon 2. So this is the total irradiance we will get due to the interference. So we know that when delta is equal to 0, 2 pi, 4 pi, we get I max, which is basically I1 plus I2 plus 2 root over I1 I2. For I1 is equal to I2 is equal to I, this became 4I naught or I. And when delta is equal to pi by 2, I is basically the addition of two intensities. For I mean, I1 plus I2 minus 2 root of I1 I2 when delta is equal to pi, 3 pi, 5 pi. When I1 is equal to I2, this becomes 0. So we can write a equation for delta and we get a plane or hyperboreal structure of maximum irradiance for two sources, which has been discussed in the class. I want to write the equation. This is 2m pi when delta is equal to 2m pi, where m is equal to 0 plus minus 1 plus minus 2, we get maxima. And delta is equal to m dash pi. You can write this m pi also, but you need to remember this m and this m. Or you can write this 2m plus 1 pi, where m is equal to 0, 1 and 2. This is the condition for minima. So basically you also need to know the condition for interference. This is also has been discussed in the class and very thoroughly. That the wave needs to have the same frequency. If they have equal or nearly equal amplitudes, and two sources needs to be in phase. So basically epsilon 1 minus epsilon 2 needs to be constant. It should not vary. So what will happen if this condition doesn't get fulfilled? You know that if it is not same frequency, you will get uniform illumination and all. And sometimes, like if fringe shifted, that's not the problem. But if we cannot see the fringe, that means there is a problem in the interference, and we will not want this kind of situation. So these are the conditions for the interference. So interference can be of two types. One is, okay, so basically this equation, corresponds to a fringe like this. This is delta and this is I. So here this is the minimum position and this is the maximum. Here this like height we have shown it's same, but in real life it's like kind of envelope due to an effect which is called diffraction. So it is some of like this. So the interference can be due to the division of wavefront, another reason is division of amplitude. So the example of this is basically biprism, Boyd's mirror, divided lens, and etc. For division of amplitude, fringes by, the examples are basically fringes by thin films, Newton's ring, Michelson's interferometer, and so on and so forth. Fabricated interferometer, ferrometer, and fabricated interferometer, and so on and so forth. So in the division of wavefront, the wavefront got divided, like you see in young double slit experiment also. This is a source, and when it falls on a slits, this wavefront got divided into two wavefronts. So this is division of wavefront. And in division of amplitude of the incident light wave is getting divided in two or more parts by partial reflection and refraction. And division of wavefront can be due to, you can do it by reflection, refraction, diffraction, by putting slates and etc. So first we have seen the Young's double slit experiment. Where it was been done in 1801. So he allowed sunlight to fall into a pinhole S, and then at some distance away on two pinholes, he placed two pinholes, S1 and S2, and finally he put a screen here and saw an interference pattern here. So in interference pattern, there is like maxima, which is a bright fringe, then minima, which is a dark fringe, and so on and so forth. So when we use white light for the Young double slit experiment, the center fringe is always white because all the wavelength falls at the same point, but the like the more we go from the central fringes, we get different maxima for different light. Like red light has maxima at different position, and blue light has maxima at different position, and so on and so forth. So interferometers can, like you will see further in the course, that interferometer can be used to determine the wavelength and very minute difference between two wavelengths. So if this distance is A, and this distance between two pinholes and the screen is capital D, and a point YA. So at YA, the path difference is A YM D, and we know for maxima to be happened. Okay, so this is the midpoint basically. So the YM is coming from this point. So for constructive interference, or to get the maxima, the path difference should be, so the phase difference should be 2m pi. So path difference is 2 pi by phase difference is basically 2 pi by lambda into path difference. So path difference is lambda by 2 pi. So for constructive interference, so sorry. So the path difference would be like this. This is R2, this is R1. So for constructive difference, the path difference should be, for constructive interference, you can see this R1 is greater than R2. So basically R2 should be m into lambda. What we get from this equation, that we know that phase difference should be 2m pi. So phase difference is basically 2 pi by lambda difference. So path difference is lambda by 2 pi into phase difference. So lambda by 2 pi into 2m pi is basically and this R1 R2 is basically this distance. And if this angle is theta, this thing is a sine theta. So the angle is so small that a sine theta becomes a theta or a tan theta, and tan theta is basically ym by d. So this becomes a ym by d. So a ym by d is equal to m lambda. So ym is basically d m lambda by a. So that y ym at, if we want to have a fringe at ym, so ym should be at the distance dm lambda by a, and the fringe width ym plus 1 minus ym, that becomes lambda. Then we see the law here. So this is let's me. So M1 and M2 is the mirror. The light coming from S1. So the light reflected from the mirror, forming an interference pattern with the light from S1 in the AE region. So when the light gets reflected, so here you need to remember that the light from S1 is in that it will go in everything from here to there, it go in this area, but it gets reflected from M1 M2, so it appears that there is a light source in S2, and the S2 light is in this portion. So in this portion the two waves get interfered or overlapped, so we get interference only in this position. So this is basically Lorentz mirror, and here also fringe width is same, which is basically d, the small d lambda. Here is the distance between the source and the distance between the sources, but here like Young's double-slit experiment where constructive interference happens when the path difference is equal to n lambda. Here the path difference, constructive interference will happen and path difference is n plus half lambda. Because of the reflection, you get to know that there is a sudden phase change of minus pi. That's why where it is supposed to be a maximum, we get minimum. And where path difference is n lambda, we get minima. This is the complete opposite of the Young's slit. Then we get another division of Wolfram phenomena in Fresnel's biprism. So in Fresnel's biprism, here it is basically two biprisms. They are joined at the base. Is two thin prisms joined at the base. A single wavefront impinges on both prisms, that is from S, and they get refracted, and they appears to be coming from S1 and S2, and again the waves coming from S1 is in this area, and the waves coming from S2 are in this area. So they got overlapped in this portion, and we get fringe in this portion. So this is the distance between two virtual sources, that is S1 and S2, that is small d, and this is the distance between the source and screen is capital D. So here also the fringe width is d by small d. Here there is no pi phase change, so everything is similar to the Young's double slit experiment. By using this Fresnel's biprism, we can determine unknown wavelength, the acute angle of biprism, and also we can always determine a thickness from the material if we use the material in one of the path. So the thickness is basically is equal to d delta by d n minus 1. So the delta is shift in fringe pattern, or we can say the shift in central fringe. So this is d is the thickness. Now we'll do some exercise that what will be the shape of fringes when two wave interferes. So consider the wave is coming from a spherical wave whose locus at 0, 0, z0 superimpose of a superposition of one spherical and one plane wave. What will be the fringe pattern? So the spherical wave, the point from where the spherical wave is in is located at 0, 0, z0. This is the y-axis, this is the axis, and a plane wave is traveling like this. Okay. So this is fringe, and we suppose that amplitude So basically for plane wave, this 1 into E. To solve these things very conveniently, we always do this calculation in like exponential form. So A cos theta can be written as A real part of e to the power I theta. Okay, this is how we can also write a wave. So the plane wave is in y and z plane. So we'll write e to the power I k y y plus k z z. If it is in 3D model, it would be an 3D model. We would also add plus kx kx. So electric field can be written as a to the power I theta. So I is equal to a to the power I theta into a to the power minus I theta. That is a square. And here a square is considered 1. Or a is 1. For spherical wave, we get a 1 e to the power I. We can write spherical wave like this, k 2z0 coming from, which is coming from 0z 00z0. So basically it should be k by r. This is z0. So from the example discussed in class 19, you get to know that this becomes k by 2 into g, which is here z0 into y square, so square plus y square. So now the intensity would be intensity of the superposition would be also equal to e to the power I k by 2z 0 x square plus y square plus e to the power I k y y plus k z z into the complex conjugate of these quantities e to the power minus I k 2z naught x square plus y square plus e to the power minus I k y y plus k z z. So k y and k z z is basically wave vector in y and z direction. So if you simplify this becomes 1, and if you multiply this becomes 1, and not indefinite metric term. The indefinite metric term is this, that is I k by 2 0 x square plus y square minus k y minus k z plus e to the power minus I k by 2z0 into x square plus y square minus kyy minus kz that we can write as, so that is basically ei theta plus e minus I theta by 2 is equal to cos theta. So we can write that as a 2 cos theta. Theta is here. K by 2z0 x square plus y square minus kyy minus kz z. So this will be the intensity, and we can say this is the phase of the interferometric term, or we can say that this is the phase basically, because only the interferometric term has the phase. So for constructive interference, we know the phase difference, which is k 2z naught x square plus y square minus k y minus kz z is basically 2m pi. So for m is equal to 1, this is basically 2 pi. So now we assume that the position of the screen is z is equal to 0. Then only remaining term are k by 2z naught x square plus y square minus ky y is equal to 2 pi. So these are basically constant. We can write as a x square plus y square, a1 and a2y is equal to 2 pi. So a1 is equal to k by 2z naught, a2 is equal to ky. So it became a1 x square plus a1 y square minus a2 y is equal to 2 pi. And this became x square plus y square minus a2 by a1 y is equal. Basically now we need to rearrange the equation and have a meaningful equation of locus, which can be like circle, hyperbola, parabola, or straight line. So after doing all the calculation, I'm doing this for you here. Again, x square y square minus 2 into a2 by 2a1 2y plus a2 2a1 whole square minus a2 2a1 whole square equal to 2 pi a1. So this is became x square plus y minus a2 by 2a1 whole square is equal to 2 pi a1 plus a2 square by 4a1 square. This whole thing can be written as a constant. So we got the equation x squared plus y minus c whole square. So c is basically a2 by 2a1. a2 is ky, 2a1 is 2k by 2z naught. So basically it is ky z naught by k, which is c, is equal to a. So basically it is a circle with radius 2 pi into 2z naught by k plus ky square by 4k square by 4z naught whole square. So that will give us 4 pi z naught by k plus ky square z naught square by 4k square. Can see for 4 if m is equal to 0, that is also a circle. So the fringe pattern are circular for a case where the spherical wave and plane wave interferes when the plane wave is at the angle and spherical wave is coming from a point in z axis, which is at z0 distance away from the screen. Second, second example where this is a screen. Here the spherical wave is coming from this point, which has x naught, y naught, z naught, and a plane wave is in this direction. Actually, the we assume amplitude is 1. Your assumption is basically amplitude is 1. So for plane wave, the electric field is basically E1 is 1 into to the power I k z, and for spherical wave E2 is that is 1 e to the power I k by 2z x minus x naught whole square plus y minus y whole square plus z minus z naught whole square. So we have seen that this doesn't survive when we simplify this equation. So basically I is basically to the power I 2z plus e to the power I k by 2z naught x minus x naught whole square plus y minus y naught whole square into e to the power minus I k z. You can consider this portion as a constant, which is going to be theta plus e to the power minus I k 2z naught means x minus x naught whole square plus y minus y naught whole square. So all the calculation, it became 2 plus 2 cos theta, where theta is kz minus k by 2z naught x minus x naught whole square plus y minus y naught whole square. So for constructive image, phase difference is 2 and 5. And for destructive image, the phase difference should be 2n plus 1 5. So for M1, n is equal to 1, we get a bright fringe. So we get theta minus k by 2z naught x minus x naught whole square plus y minus y naught whole square is equal to 2 pi. After all the simplification, we already got the terms x minus x naught whole square plus y minus y naught whole square is equal to theta minus z. So it's also start videos. Root theta minus 2 pi into 2 z naught by k. For m is equal to 0, this becomes 2z naught theta. Okay. So if the spherical wave is coming from a point which is at z naught and another spherical set of spherical waves coming from z 1, then also the fringes will be circular. You can try it your own, but if these 2 points are situated like this, x naught, y naught, z naught, x naught, minus y naught, and z naught, because this is x direction, this is y direction, this is z direction, only y is in the opposite direction. We get fringes which are not circular but the straight line. If we do the calculation, we will get this part. So we will do the calculation minus. So the equation for x naught, y naught, z naught is 1 e to the power I k by 2z naught x minus x naught whole square plus y minus y naught whole square. The wave situation for of 0 point is 1 for I k by 2z naught plus it would be x minus x naught whole square plus y plus y naught whole square. So when you add those two things, the intensity became 2 plus 2 cos k by 2z naught x minus x naught whole square plus y naught whole square minus x naught whole square minus y naught whole square. So the resultant became 2 plus 2 cos 2k z naught y minus 2y naught. So this is basically calculation of a straight line. For constructive fringes, 2k Z naught y is equal to y naught is equal to 2f pi is the equation for destructive fringes. Y is 0 and then 2 plus 1 5 for n is equal to 0 we get, see, y naught z naught is a constant, k is constant, so y is equal to 0, that is x-axis or z-axis. So here we get three kind of situation. For a spherical wave, first one, thin wave spherical wave superimpose with a circle, and it doesn't depend on where. You can like imagine many other kinds of like position of the spherical wave coming from, and so from here the spherical wave doesn't go like this. It's basically follow same way. So the angle doesn't matter for spherical wave, but for plane wave that gets reflected in kx, ky, kz component. So what is a circular fringe? And when the 2 points are like this, we also get circular fringe, but when the 2 points are like this, situated in plus 1, y naught or minus y naught, results in a straight line. Now we go to some question. Some very basic questions. That is one, in Young's double slit experiment, notably, Young's double slit experiment, the separation between the slit is 1 millimeter and fringe spacing is 0.5 millimeter. on screen kept at a distance of 1 meter from the slits. Find the wavelength of the light. So the fringe spacing is fringe width. So fringe width can be written as beta. Beta we know lambda d by small d. So lambda is equal to beta small d by d. If we put all this value in same uh, domination, that is millimeter or meter. So write all this in meter. So the result will be minus 3, 1.2 into 10 to the power minus 3 to 1 meter. That is basically 600 nanometer. So the fringe width is 600 nanometer. Now question 2, which is in a Lloyd's mirror experiment. Calculate the ratio of the intensities at for interference maxima and minima if the mirror reflects only 75% of the light incident on it. So the light, 5% of the light get reflected. So the reflectivity R is basically 7 that is 3 by 4. So reflection coefficient is root over R, which is root over 3 by 2. So let's say A1 is the amplitude of direct beam. Then A2, the reflected beam, become A1R, which is A1 with 3 by 2. So I maximum will be summation of 2, which is A1 plus A2 whole square, and A1 minus A2 whole square, which is 1 plus R whole square by 1 minus R whole square, which is 1 plus 3 by 2 whole square. by 1 minus v3 by 2 whole square. Now if we put the value and all those things, that will be 194. This is the answer. Now question 3. Lloyd mirror experiment is done with plain metallic sheet and a microwave source of wavelength 40 centimeter. So the metallic sheet and the lambda is 40 centimeter. If the source is 6 centimeter above the plane of the sheet, of first maxima above is plane at a distance 4 meter from the source. So in this question, so we say that P is the basically the position of the first maxima and CP is X. Then we need to know that S2P minus S1P it should be 2 because for n is equal to 0 we'll get the first maxima. After in S1P, and if we simplify that, S2P would become D 1 plus half of x plus d by 2 by d whole square. S1P become 1 plus half of x minus d by 2 by d whole square. So S2P minus S1P becomes x small d by d. That should be lambda by 2. So x is equal to lambda by d by 2d, lambda d by 2d. So when you put this value, lambda is okay. Lambda is 40 centimeter, and here it is mentioned that the source is 6 centimeter above. So this is d and this is d by 2. This d by 2 is 6 centimeter. And another thing is d is capital D is 4 meter. So x becomes lambda d by 2d. Therefore, x is equal to 666.6 centimeter. So this is the distance of first maximum. Now we'll go to the next question. That is the acute angle of by of refractive index 1.5 is 2 degree. As slit is illuminated by monochromatic light is placed 10 centimeter from the biprism. If the distance between the two dark fringes observed at a distance of 1 meter from the biprism with an is 0.18 millimeter. Find the wavelength of light used. Basically, here we want the refractive index of the biprism and then the slit is placed 10 centimeter from the biprism, and that the distance between two dark fringes is at a distance 1 meter. This is 1 meter, and the fringe is 1 meter. So answer, that is, we know D is between distance between the virtual sources 2a n minus 1 alpha is equal to 1.5 alpha is equal to b, which should be converted into radian, and a is 10 centimeter. So a is basically distance a. This is d by 2. So a is basically 10 centimeter. So d became 0.349 into the power minus meter. And here also, if we do it, meter is lambda d by small d. So lambda is equal to beta small d by d. Putting all this value on 9 10 to the power minus 2 by 1.1 in meter, we get lambda is equal to 571.2 nanometer. Now another example is measure the thickness of thin film glass. Fringes are produced with monochromatic light. Wavelength 689 nanometer are thin film of class of Ri refractive index 1.52 is placed normally in the path of one of the interfering central right. Right fringe is found to move to a position occupied by the fifth right band. from the center. Calculate the thickness of the glass. So basically, glass. So the center light fringe is supposed to be like this, that shifted to the fifth position. So basically, this extra optical part, which is n minus 1 p, should be equal to m lambda, where m is 5. So t is basically 5 into 6, 8, 9 to 10 to the power minus 9. So when it was central fringe, it should have been 0. But because of this extra optical path length, the m has moved to from 0 to 5. That's why it was written n minus 1 into t into m lambda, because this is the extra path of the optical path difference, and due to this extra path m moved, that is the m movement. Actually, that should be equal to delta m lambda. So here delta m is equal to 5. And putting all this value in meters, we know the thickness is 6.625 into 10 to the power minus 3 millimeter. That is the answer. Number 6. In a Fresnel's biprism experiment, the base angle prism is 3 degree, and the refractive index of glass is 1.5. Interference fringes are formed with a source of wavelength 600 nanometer, located 10 centimeter from the biprism. The screen is placed at a distance of 1 meter from the source. Find the maximum number of fringes that can be observed. So basically, this is the picture that tan delta should be equal to, that is delta is equal to d by 2. So d is equal to 2 delta into a, that is 2a in minus 1 alpha, and fringe width is beta equal to lambda a plus b by 2a n minus 1 alpha. So d is equal to actually a plus b. So maximum fringes EF by B. So yeah, EF is the total length of the area, and B is the fringe, beta is the fringe width. So number of fringes should be divided by this, and we will get the number of fringes. Is basically A. Is 10 centimeter, B is 90 centimeter, so A plus B is equal to 1 meter. Lambda is 600 into 21 minus 9 meter. N is 1.5. Alpha is 3 degree, that is 3 into 5, 180. So beta is equal to 600 to 10 to the power minus 9 to 1 into 180 by 2 into 0.1 into 0.5 into 3 power, which is 11.46 10 to the minus 5 meter. So we get beta is 11.46 into minus 5 meter. Here number of fringes is EF by beta. So EF is equal to basically B into 2 delta by beta. See, this is EF, this is B, and this is 2 delta. So EF is B into not beta, that is B into 2 delta. So this is 2b n minus 1 alpha. Beta is 11.46 into 10 to the power minus 5. So that is 411. So in EF region there should be 411 fringes. A similar question in the Lord's mirror. So here mirror length Lord's mirror is proven. The mirror length is 5 centimeter. Illuminated with light of wavelength. Lambda is 589 nanometer from a narrow slit point 1 centimeter from this plane. So divide to 0.1 centimeter this plane and 5 centimeter measured in that plane. And so this is centimeter. So A is equal to 0.05 meter from its near edge. Find the fringe width on a screen placed 1.2 meter from the slit. So basically D is equal to 1.2 meter and they determine the maximum number of observable fringes. So let me put the question here. First, when 5 centimeter is illuminated with a light of wavelength 589 nanometer from a narrow slit 0.1 centimeter from its plane and 5 centimeter measured in that plane from its near edge. Find the width screen placed 1.2 meter from the slit. Also determine the maximum number of fringes observable. So similar, we need to find the delta beta, which is lambda t by small d. Putting the value, we get 3.34 millimeter. Then we need EF by beta. So EF is this distance. So we need to find CE, and EF is CF minus CE. So CE basically B tan theta 2. Yeah, CE basically tan theta 2, and CF basically B plus L, this distance is L, B plus L tan theta 1. D minus A tan theta 1 minus D minus A minus N tan theta 2. So theta 1 is equal to theta, which is D plus B, like here this is theta 1, this is theta 1. So theta 1 basically D by A, and D by 2 by A, and theta 2 by D is equal to D by 2 by AL. So putting all this value, D minus A into D by 2A minus D by 2A plus L. So L is length of the mirror. So basically that is equal to 0.05 meter. Putting all this value, we get EF equal to 1.2 centimeter. The number of fringes, basically EF by beta, that is 1.2 centimeter by 0.0534 centimeter, which is equal to 34. So we will get 34 fringes. So basically these are the more complex question we will get from this double lyrics, humanoids, mirror reference by prism. Other questions asked in the quiz is basically from the uh, lecture slides. If you go through the slide, and I have discussed those things briefly at the beginning of the class, it will be easy to solve those questions. Uh, Thank you. That's for today.